This video picks up with the topic of ANOVA, where we're going to look more in depth at the logic of ANOVA and the formula used to calculate all the quantities needed to calculate the F ratio for our test of significance. Hopefully you remember that analysis of variance is a kind of statistical test that we use when we have two variables where our dependent variable is continuous and our independent variable is a discrete variable that has three or more categories. The logic of the test and our first introduction to general linear modeling is shown in the equation at the top of this slide. Let's walk through those pieces and see what they mean. This expression is y sub ij is equal to mu plus alpha sub j plus e sub ij. Y sub ij is just a single measurement on whatever it is we're interested in. For example, it could be an individual student's exam grade. Maybe they got an 85 on an exam. Mu, as you understand, is an average. This would be the average of all the students who took the exam grade. For example, maybe the average exam grade was 75. This would tell us that this particular student is above average. Alpha sub j is our group effect. Group effect would be our independent variable. In the context of a statistics class, it might be what lab you're in. Or let's say we have 4 labs, and some labs do better than others. Historically, I would say the 8 a.m. labs, the students tend to do a little bit better in the class than students who are in the 2 p.m. labs. I'm not exactly certain why, and the scores are not dramatically different, but on average, people in the early labs do better than people in the later labs. And then finally, we have an error term, E sub I sub j. So we can see that every student's individual score is made up of 3 things. The overall average. So if a student said to me, "Can you please tell me my exam score?" and I didn't have my grading sheet with me, I might say, "Well, I don't know your score, but I know what the average was, and that was 75. You can see that I haven't gotten their exam score exactly right, but I'm as close as I can be without knowing any additional information. Maybe I know that depending upon the lab they're in, there are some lab differences, with earlier labs getting higher scores than later labs. And I say to the student, "Well, are you in that 8 a.m. lab?" And they say, "Sure." Then I would take that average exam score, 75, and I would increase it by the group effect of being in that early lab, maybe 4 points. And I'd say, "Well, I don't know your exam score exactly, but my estimate is going to be 79. And in this case, because there's a slight group effect, I've made a slightly better estimate." I still didn't get their exam score exactly right, and there's something left over, which is the error term, the amount by which I'm wrong. The error term is basically the difference between my predicted value based on the group mean, on the overall mean, and based on the group effect. It's the part that's left over, and we often refer to that as the residual. You can see at the formula at the bottom of this slide that the error term is equal to the individual score minus our model, which is mu minus alpha sub j, where again alpha sub j is our group effect. Of course, it's possible that there is no group effect and that alpha sub j is equal to 0, and that is knowing what lab a student's in would have no effect on my ability to improve my prediction of an individual score. Here's our ANOVA table and all the formulas in it. This is our first introduction to a little bit of advanced summation notation where we have double summation. We'll have a video on this that we'll make available to show you how double summation works, but at the heart of this particular slide is that some of these quantities take into account what group a person's in, or what group an object's in. This is particularly important for the between and within. The total sum of squares actually ignores group membership. So let's look at these formulas one at a time, starting at the bottom with the total sum of squares. That formula for the total sum of squares should look somewhat familiar to you. If we didn't have the double summation, you'd see that that sum of squares is simply the numerator of the variance for the dependent variable. That is, it's each score, y sub I, minus y bar squared, and then we sum all those individual squared differences. If we took that particular value and divided by n minus 1, we'd have the variance, and of course if we took the square root of that, we'd have the standard deviation of the dependent variable. The only difference between this formula and that variance formula is that we're keeping track of what group a student's in, or what group an object's in, by using that J counter, which signifies groups. Groups in ANOVA are often signified by the letter J, and in the case of statistics labs, if I have 4 labs, J would equal 1, or 2, or 3, or 4, depending upon what lab I'm looking at. If we move up a little bit and we look at the within group sum of squares, we can see that this looks very similar to a variance as well, except instead of looking at the difference between an individual score and the overall or grand mean, we're looking at the difference between an individual score and the mean of a group. This would be like saying, let's isolate your lab and measure the variance simply within your lab and ignore the other 3 labs. Of course, we're going to have to square these differences because we know that the sum of deviations around a mean is always equal to 0. And then we're going to do this for all of the labs. And that's where that other notation sign, the other sigma, comes in, where we do it first for lab 1, and then for lab 2, and then for lab 3, and then for lab 4. Let's look at the between group sums of squares next. This is in the top line of the table. You can see here, once again, this looks like a variance, like the numerator of a variance, and in fact it is. Here we're taking the mean of each group, y bar sub j, so in the context of this example for labs, the mean of lab 1 minus the overall or grand mean, square that difference, the mean of lab 2 minus the overall grand mean, square that difference, and so on. So we have 3 different variances here. The total sum of squares is the variance of all the cases or of our dependent variable. The within group sum of squares is a variance, an estimate of the variance that's based on different subsamples. J equals 1, group 1, J equals 2, group 2, and so forth. Our between group sum of squares is the variance of our averages of groups around the grand mean. These 3 values form an additive scale, if you will. That is, between plus within is equal to total. If we take whatever value we calculate for the between group sum of squares, add that to the within group sum of squares, we get the total sum of squares. And therefore we know when we're calculating these sets of numbers, if we have 2 of those 3 numbers, we can calculate the third as a difference or as a sum. For example, the between group sum of squares is typically the easiest thing to calculate because there's the least calculator entry involved. So I always try to calculate that between group sum of squares if I can. The total sum of squares is relatively easy to calculate because we've done that in class and in labs. And if we just ignore our groups and just calculate the straight numerator of that variance, we know how to do that pretty easily. We also know that total minus between is equal to the within, and therefore I can calculate that difference and get my within group sum of squares without a lot of effort. Moving over to the next column, we see it's labeled degrees of freedom. There's a number of degrees of freedom associated with each one of these estimates of variances. We already know or have been exposed to the total sum of squares that its degrees of freedom is n minus 1. That's the number we use to average out that numerator to get our overall variance. Our between group sum of squares is pretty easy. However many groups we have, so if we're using this example of exam scores and labs, we have 4 labs, we have j minus 1 degrees of freedom. And then finally, we have the within group degrees of freedom, which is our number of cases minus our number of groups. This column is additive as well. That is, the between group degrees of freedom plus the within group degrees of freedom is equal to the total degrees of freedom. And again, since if you know any 2 pieces of information in that column, you can calculate the third. Moving over now to the column labeled MS, we can calculate what are called mean squares. If we take each sum of squares and divide by their associated degrees of freedom, we're calculating an average or mean square. So we have our SS column, our sums of squares, between, within, and total. We have our degrees of freedom column, 1 for between, 1 for within, and 1 for total. And if we take our sums of squares and divide by their degrees of freedom, we get our mean squares. Finally, if we take those two values and calculate the ratio, ms between divided by ms within, we get our F statistic. The point of this table really is simply to organize these numbers in a logical way. We know that the first two columns, the sums of squares columns and the degrees of freedom column, are additive. Between plus within equals total. We know that our ms column is equal to each sums of squares divided by their degrees of freedom. And finally, if we take the ratio of those two mean squares, we get our F statistic. That's the statistic that we will use in our hypothesis testing framework, that after we calculate F in step 4, we'll use in step 5, we'll compare it to some predetermined or critical value of F to see whether it's large or small, statistically speaking, and whether we reject or fail to reject the null hypothesis. Down at the bottom of this slide, you'll see a set of data labeled F, N, and S are the columns, and they have different numbers in them. And this is an example we'll go through in another video, but you can see the resulting output from Stata, a statistical software application that I like, and you'll see that it's laid out in exactly the same format as the table above. It tells us the source of our variation, between, within, and total, has a sums of squares column, a degrees of freedom column, a mean square column, an F statistic, and then for us, because we like using these computers where they can do additional things for us, we get a p-value. So we could either compare that F statistic, that 5.89, to an F statistic from a table in the back of the book, or we could compare that particular p-value, 0.0075, to a predetermined p-value from our hypothesis testing framework. Say, for example, we set alpha equal to 0.05, we would reject the null hypothesis in this particular case. Now, we didn't describe what this example is showing us, how things are measured, and so that it's a little hard to understand in the abstract, but one of the interesting things here is if you understand the concept of a p-value, then even though you don't necessarily know how to calculate this F statistic, you could do a test of significance based on the information in this statistical output. Why are all those sums of squares additive? How does that work? How do we go from that linear model where we have an individual measurement or a measurement of an individual broken down into a mean and a group effect and error? Let's take a look at a little bit of a math here and a little bit of theory. You can see the total sum of squares on the left. It's the same sums of squares that was in the slide just before. If I strip out all the summation, so I'm only going to look at one individual case, and I get rid of all the squares, the square, then I can rewrite that as y sub ij minus y bar is equal to y sub ij minus y bar. So we preserve the equality. I'm now going to take a constant, y bar sub j, the mean of group j, and immediately add that in and then immediately subtract it out. That's called completing the square. You may have seen that in other math courses you've taken. And once I add in that constant and subtract it out, which keeps our equality okay, I can rearrange my terms, which you see in the next line. I now have y sub ij minus y bar is equal to the quantity y sub ij minus y bar sub j plus y bar sub j minus y bar. I'm not interested in just an individual case, so I'm going to put my summation sign back in. And I know that if I take deviations around averages, they sum to 0, so I better put those exponents back in. And we find out that our total sum of squares is equal to some part that is with a within group sum of squares and some part that is a between group sum of squares. And more importantly, we can see that the between group sum of squares is the part that's due to the effect of being in a group, which is the thing that we actually want to test. So some people call this the decomposition of variance, which is a pretty good way of thinking about this. I have a dependent variable, say exam scores, that has some amount of variation. It has a standard deviation, it has a variance. Some of that variation can be attributed to within group sums of squares, basically error, just differences within group. Some of the variance could be attributed to a group effect, the difference between being in lab 1 compared to lab 2, compared to lab 3, compared to lab 4. Of course, if that between group sum of squares is small or 0, we'd say there is no group effect. Our test of significance is a test of whether there is a group effect or not. So, if the null hypothesis is true, we should observe equal means in each of these groups. And if we were to observe equal means in all these groups, then the mean of all those means would equal the grand mean. So if we think about this in the most extreme situation, the sums of squares between could be equal to 0 if there's absolutely no group effect, which would mean that our within group sum of squares would have to equal the total sum of squares. That's equivalent to saying knowing group membership does not provide any information that would allow me to make a better estimate of the dependent variable. Everything that we observe is simply due to error or chance. We have these different estimates of these variances, one called between and one called within, but they're really based on different metrics. One is about the differences in averages compared to of group averages compared to the grand average, the grand mean, and some are individual differences compared to, or individual scores compared to means within group. So if we average them out by their degrees of freedom, they should provide us similar estimates of the variability of our dependent variable. So we'd like some way of evaluating whether these two statistics are equal to each other. Once we average them by their degrees of freedom, they're really measuring exactly the same thing. And therefore, we could take the ratio of these two things to see if one is larger than the other. We'll always take the ratio of the mean square between to the mean square within because we're always testing whether there's a group effect and whether the group effect is greater than the within group effect. So if we take the ratio of MS between to MS within, we calculate what's called our F statistic. Now, let's link this back to our sampling distribution discussion earlier. We know that if we have single sample means or difference of two means, our picture of chance is probably going to be the t distribution, although there may be situations where we could use the z distribution. But mostly we're going to be pretty comfortable using t. That is, we know that sampling error or chance has a very regular pattern if we look at repeated random samples, and that pattern is basically a normal distribution. If we take repeated random samples and calculate MS betweens and MS withins and calculate the ratio of those two values, there is also a very particular pattern. That particular statistic has an F distribution, and it's not normal. It's different in several ways. For example, it can never be negative, whereas our normal distribution or our t distribution, when we convert things to z-scores, can be negative. An F statistic can never be negative. And an F ratio equal to 1 is consistent with chance, where 0 would be consistent with chance for our t distribution. But the point is the same, that whenever we have a particular kind of statistical problem, continuous dependent variable, discrete independent variable that has 3 or more categories, we know that we can calculate what's called an F statistic, and that the appropriate picture of chance to compare that F statistic to is the F distribution. So here's our table. Hopefully going back to this and reviewing it one more time will make more of this concrete, and we're going to provide an example in an upcoming video. Again, this particular ANOVA table, all ANOVA tables are laid out in a very particular way, such that the first two columns, the sums of squares and the degrees of freedom columns, are additive. SS between plus SS within is equal to total. The degrees of freedom between plus the degrees of freedom within are equal to total. If we take those total sums of squares and divide them by their respective degrees of freedom, we get what are called mean squares. Both of those are estimates of some kind of variation of that overall variability in our dependent variable. If there's no group effect, our between group sum of squares and our within group sum of squares should be similar magnitude. And therefore, when we calculate the ratio of those two values, if there's no group effect, we should see a value of 1. As we start finding group effects, or as group membership becomes more important, the between group sum of squares will be greater than the within group sum of squares, and our ratio will get larger than 1. At some point, we may find that that particular ratio is large enough for us to conclude that we don't think chance is operating, that group membership is not having an effect. We think that group membership does have an effect, and it will lead us to reject the null hypothesis. In the next video, we're going to provide an example based on a real research experiment that will show you how ANOVA works, what the data look like, how to calculate all the numbers in this particular table, and how to use the F table in the back of your book to look up F critical. We'll then take all that information and put it into the hypothesis testing format and show you how to make a statistical decision about this kind of problem. I hope you enjoyed the video, and as always, if you have questions, please let us know.